Hi everyone, thank you for listening to our talk about optimizing tail latency for highly dispersed data center workloads. My name is Max, and this is joint work with my colleagues at Penn, MIT, and MSR. First, I will give you some background on microsecond scale data center systems. Today's cloud applications can be very fast. For example, in-memory databases can serve GET requests in single-digit microseconds. Likewise, fast machine learning inference engines can serve requests in tens of microseconds. At the microsecond scale, variation can be particularly extreme in processing times. In the case of the in-memory database, while some requests can be served in single-digit microseconds, more complex range queries can run in hundreds of microseconds, if not milliseconds. And we know from both theory and practice that if we have a suboptimal scheduling policy for these workloads, we will incur high tail latency. High tail latency in this case refers to the fact that some requests are going to experience vastly slower response times than lower percentiles, such as the median. If we look at the landscape of microsecond scale scheduling in both industry and academia, we notice that most systems attempt to approximate some form of first-come, first-served policy. On the left is pictured receive-side scaling, a technology widely available in the data center today. RSS dispatch requests directly into worker cores. Unfortunately, if the processing time is not uniform, meaning that roughly all the requests don't execute in the same amount of time, RSS will lead to situations where some cores are overloaded while some others are idle. Now, the recent ZigOS and Shenango systems have been alleviating this problem by approximating a centralized first-come, first-served policy. What they do is, through work stealing, rebalance work from overloaded workers toward idle workers. But this will still lead to situations where all the cores could be busy processing long requests, and if a burst of short requests shows up in the system, they'll have to wait. If the workload is heavy-tailed, they might have to wait for a lot of time. In theory, we know that the ideal scheduling policy for such workloads is some form of time sharing, meaning that we can swap out long-running requests so that we can execute the shorter ones. But at the microsecond scale, these policies are very challenging to implement. Recently, the Shinjuku team has accomplished the feat of bringing preemption to the microsecond scale. Their system can preempt as frequently as every 5 microseconds. But for requests that execute in single-digit microseconds, these are still significant overheads, as we show in the paper. In our research, we explored the design space and proposed a solution that vastly improved the quality of service of short requests without relying on preemption. We proposed DARC, standing for Dynamic Application-Aware Reserved Cores. DARC asks for programmer to declare simple request classifiers such that it can filter requests based on their type. DARC will then profile the CPU demand of each request type, identify the ones that are shorter, and reserve them some cores. All the while, it will be able to handle bursts for most of the types of requests and minimize CPU waste. The two key insights of our system is that by keeping some core idles, we can prevent head-of-line blocking from the longer requests. By doing so, we'll be trading off some overall throughput to improve the latency of short requests. Here is DARC's scheduling model. Like Shinjuku, we dedicate one core to dequeuing requests from the network card. We'll then apply the request classifier so that we can identify the request type and steer the request into typed queues. Now, DARC, that I will describe in the next slide, will proceed to some reservation steps where it will attribute some cores to some types of requests. And then it will dequeue requests from each queue, proceeding with the shortest request type first and going toward the longer request types, and dispatch them to the worker cores. Here is Dark's scheduling policy. After profiling the CPU demand for each request type, Dark will regroup together requests of similar processing times. It will then attribute a set of core to each group of requests, shortest group first. And during this allocation step, Dark will tune work conservation by enabling cycle stealing from shorter groups to slower groups. Here is a case study using the TPC-C workload. TPC-C is made of 5 request types. This request type executes in roughly 5 to about 100 microseconds. The payment and new order requests are making up 88% of the workloads, and these are some of the shortest request types. We are able to extract the average CPU demand of each of the request type so that we can get an idea of how many cores we should attribute them. Dark will regroup together requests of similar processing time. So the first group will be made of payment and order status requests, and then attributes the summation of the CPU demand of each of the type, with some exceptions that are detailed on the paper. So in this case, the first group will receive 2 cores, but will enable cycle stealing for this group, and they will be able to execute on the 12 other cores of the system. The second group, made of new order requests, will receive 6 cores and be enabled to steal cycles from the 6 remaining cores of the system. These remaining cores are otherwise attributed to a group made of delivery and stock level requests. Here's a first look at Dark's performance. We want to answer 2 questions. How much do we improve short request quality of service? And how much sustainable throughput do we lose by doing so? We'll be using a simple workload made of 50% short requests running in 1 microsecond and 50% long requests that are 10 times slower. Here are the results. The way to read this graph is as follows. The leftmost column is the overall slowdown in the system. Slowdown is computed by taking response time and dividing it by nominal service time. This gives us an insight of how much queuing happens in the system. The middle and rightmost column are representing the tail latency for the short and the long requests, respectively. The x-axis is the total load on the system. The ideal behavior is that as the load increases, we want to keep slowdown and latency small. In fact, we notice that Dark is able to improve slowdown over centralized first come first serve by almost 16 times. And it does so at a small cost of 5% throughput for the long requests. Please go read the paper for more results. We've been evaluating our system against Shenango and Shinjuku and have some interesting results. Now I'll conclude the talk with some takeaways. We proposed a system that optimized tail latency for heavy-tailed microsecond workloads without relying on preemption. Dark is a not work-conserving scheduler. It trades off some throughput for improved short request latency. Finally, our research reinforced the known fact that techniques designed for millisecond scale do fall short at the microsecond scale. I'll now be happy to take any question. Thank you for your time and attention.